lecture today is 4.3, the next section, linear independence. Looks like a fancy word, right? So we're going to have to explain a little bit what that means. Okay, let's look at some examples before I start saying exactly what this is. Well, we have already now discussed what vector spaces are, and we saw that R square is a vector space that we call the plane, and we have the coordinate system, and we represent vectors. Let's do this now, always with the beginning point in the origin. So let's look at this vector here, whose endpoint is 1, 0. I'm going to call this I, the vector I. It's a special vector, and there's another one, of course, that you can think of. Another special point would be the point 0, 1 here, right? And so this would give me the vector J, I'm going to call. And they kind of are important, nice vectors, because if I now take any vector, so let's take another vector here, I'll do this one here. I'm going to try to kind of eyeball it a little bit, let's say, okay, go a little bit further. So let's say that this is 2 and this is 3, so this is the point 3, 2. Okay, so this is the vector. So let's call this U. Then we see actually that we talked about linear combinations, right? We have talked several times about this, and what I'm claiming is that U can be written as a linear combination of I and J. So that means I have to find some coefficients here, that if I put them there, then I get U. But it's quite obvious what you have to do, right? Because the first coefficient you need is 3, so I'm going to just put a 3 here. And the second coefficient is a 2, so I put a 2 here. Because remember, I is 1, 0, and J is 0, 1. And if I work this out, I get exactly 3, 2. So it is, at the one hand, clear that every vector that I take can be written as a linear combination of these two guys. And it's actually even immediately clear how to do that. We had homework problems from last time where it was the case that you could write a vector in a linear combination of others, but it was not obvious how to do that. So this makes these two vectors kind of quite nice. And in fact, another thing that you should notice is there's only one way of doing that. This is the only combination, linear combination, that is going to give me U, right? It's exactly that. The 3 and 2 are the coordinates. There's no choice I have here. And that's going to be something that we will discuss in the next section, which is called basis. But let me give you an example. Let's go to R3, which is also a vector space. So now we have 3 axes, if you want. Let me not put the error here, because it gets a bit confusing then. That's not a vector. So we would have similarly these nice points, right? 1, 0, 0 here. And then this would be, so if this is the x coordinate, this is the y coordinate, so that would be 0, 1, 0. And this is the z coordinate, so this would be 0, 0, 1. Okay? So we have again the 3 vectors that I will call I. This was J, okay, we all know our alphabet, right? So the next one is K, okay. And it's the same thing, right? If I now take any vector in this 3-dimensional space, okay, take a vector here, okay, you remember that I'm not very good in drawing, so this is a point here, let's say with coordinates 3, 1, I don't know, 0, 3, 0, 1, I guess. Right, so it actually lies in what plane, right? 0 means it lies in this coordinate is 0, so that it means we're lying in the xz plane, right? So this was the x coordinate, this was the y coordinate, the z coordinate, and this was the y coordinate. Okay, so 3, 0, 1. Well, how can I write this vector? So this is this vector, right? So how can I write this? Well, I can write this. So let's call this U. U is 3 times this one, plus 0 times that one, plus 1 times the last one. Exactly as before, right? Because if you work this out, this is 3 times 1, 0, 0, plus 0 times 0, 1, 0, plus 1 times 0, 0, 1. That's exactly what U is. Okay. But what about... So what this tells me, just in terms of what we just discussed in the previous section, this says that the span of I and J is actually the whole space. And this tells me that the span of I, j, and k is the whole space. But let's now look here, what's the span of just I and j? Can you see what it is? Well, it means that if I and j, how does an element look like? Well, it will be A times I plus B times j. Sorry, no underline under B, right? Sorry. B times j, where A and B is just real numbers. So this would be A times 1, 0, 0 plus B times 0, 1, 0. That means A, B, 0. So this is the endpoint or the vector. It's the same thing for us, right? If this vector lies in here, then its endpoint must be z. The third coordinate must be 0. In other words, it's the z-axis. It's 0 on the z-axis, so it lies actually. This tells me that this is the xy plane. Okay, last time we discussed that actually the spans of vectors in three-dimensional space, there are 3 types. You can have a line, you can have a plane, you can have everything. Well, there are 4 types, I guess. You can also have just a 0 vector. Okay, so so these are an example of 2 vectors that don't span the whole thing, but they still have a very nice property. Namely, if you take anything in the plane. So let's now take one in the plane. So I'll make this a green one. So this is a green vector in the plane. Let's pick it somewhere here. So say its coordinates are 3, 5. Okay. No, I mean I guess I should go up. Let me do it. No, sorry. So let's call it, it's O. So somewhere this supposed to be, I guess, the y coordinate is 2 and the x coordinate is 4, something like that. Okay, all right. So let's do this vector. Let's call it v because we have already u. Well, v can now be written. It's in the span of I and j, and what is it? 4 times I plus 2 times j, right? Sorry, 4. In the plane, I'm putting it in the plane, but that's the third coordinate here, right? I'm sorry, I apologize for this. So here we have the 0 coordinate because it's in the xy plane. So that's why there's a plus 0k, so we don't need that. And so this vector can be written is a linear combination of I and j. In other words, it's in the span. It's in the xy plane. But again, it can only be written in one way. These 4 and 2 are its coordinates. I cannot choose anything else. And so that's what linear independence is about. So, okay, so what does it mean is we say that, so I'll give you the definition. If we have an arbitrary vector space, so V is a vector space, but for us, this means, we won't see many really other examples. This means R2, R3, R4, and so on. Okay, we have vector space and we have vectors. So we have vectors v1 up to vm. There are m many. So these are vectors are linearly, well, I have to define, right, the term is linearly independent. But I'm going to first say what it means that they are linearly dependent if one is a linear combination of the others. So if one of them, I'm not saying the first one, I'm not saying the last one, it's if there is one of them that's a linear combination of the others. So let's take an example of what that would be. We haven't seen this here, but here's an example of what that would be. So I'm going to now look at an example in R square. So if V is R square, well, I'm going to take a simple example. Remember we had I, that was 1, 0. We had J, that was 0, 1. And let's just, for the simplicity, take U to be the vector 1, 1. So this would be this guy, right? So this would here be my U now. Okay, let me erase the other U that we don't get confused. Okay, so I'm claiming this is not linearly, this is linear dependent. This is an example of linearly dependent. Let me write out the word perhaps, because then should see it first written once completely, right? Linearly, an adjective, right? Linearly dependent. Namely, and I'm claiming this one is a linear combination of the other ones, which each you take one, right? Coefficients 1 and 1. So, I mean, normally we don't write it, we just write it this way, right? But this shows you that U is a linear combination of the two others, and that makes it linearly dependent. So why the word dependent? Okay, this guy depends on these two, and why linearly? Well, it's a linear combination. Okay, just think about it that way. Okay, so so that's an example of what it means to be linear dependent. In some sense, it means one of them is superfluous. You should not put it there because you can write it in terms of the others. Somehow you want to be as economic as possible, right? And this is exactly what linear dependence is about. It's saying, oh, you have too much. You some of them you can write in the, so you can drop them because you can write them in terms of the others. Now it might be not so clear, and it's also something that not always the case, but in fact, it's not just that U is a linear combination of these two. I claim that J is also a linear combination of U and I. Now, that one you might have to think a little bit about. Let's say this is U1, this is 1, 1, and this is 1, 0. But it's not so hard, right? If I subtract U from I see that I get a 2. Of course, that I could have immediately got it from here, right? I could solve in this equation. Okay? All right, so that's the notion of linear dependent, but the title is linearly independent, right? So it means not that. So what does that then mean? That means another way, so V1 and Vm are linearly independent if they're not linearly dependent. Okay, it's the negation of the previous thing. But now I'm going to tell you what it actually means. Means, okay, perhaps I'm using the word or should not be so. Means that if you have a linear combination, K1 V1 plus Km Vm, that actually gives the zero vector. So a very special case of a linear combination, right? We haven't really talked about it, but notice the examples that I took here were always non-zero vectors, right, here. But if I take the zero vector, how can I write the zero vector in terms of I and j? Well, that's 0 times I plus 0 times j. And of course, you see that if whatever vectors you take, you can always write 0 as a linear combination of these vectors, right? If any vectors, you can take 0 is 0 times v1 plus 0 times vm. This is somehow the dumbest thing you can do. And this says, if you have something that gives you 0, it's because it's the dumbest thing you can do. Then k1, k2, they all must actually be 0. There's only one way to get a 0 vector is by having 0 everywhere. In other words, there's no other way of doing it. And that's, you have to think a little bit about it, and I'm not going to explain it. The book gives an explanation for it. That is exactly the same as being linearly independent. In other words, being not linear dependent. Okay. But that gives us a way of trying to figure out whether vectors are linear independent or not. So let's now look at some examples. Let's take here. So I'm going to look at this example. So I'm going to go work again in R3. And the vectors I'm thinking of is V is the vector. I'm going to write it. It's easier to write it as rows, but of course, you remember that when we do calculations, we often work with columns. So 5, 6, minus 1, and V3, sorry. V3 is 3, 2, 1. So what does it mean for this to be linear independent? It says that, well, if you have k1 v1 plus k2 v2 plus k3 v3 equals 0, then actually k1, k2 and k3 must be equal to 0. Okay, so let's write that out, what this means here. Now it's again simpler if I'm gonna now write out with in columns. Okay, so what does this mean? I mean, let's write out what this linear combination means. This means the first one, remember, it's k1 times 1, so k1 plus 5 times k2 plus 3 times k3, and then the other ones we do the same thing, minus 2k1 plus 6 times k2 plus 2 times k3, and the last one is 3 times k1 minus k2 plus k3. And we are saying that this has to be the zero vector. What is that? That's 0, 0, 0. So what this actually is a linear system of equations. Right? This gives me, look, let's make it into a linear system of equations. Get rid of this one here. And then we write it like this. This is 0, this is 0, and this is 0. So we get the linear system of equations, and what we need to say, what we are claiming is there's only one solution, namely this is a solution. So to show that, so the question, or no, let's say, let's put it more as a question. Does this have more than one solution? It has one solution, namely 0, 0, 0. But if it has more than one, then these guys would be linearly dependent. So perhaps a little bit more, okay, don't get confused by the negations here, right? Does it have more than one solution? Then it's linearly dependent, because that gives me a dependence relation. I'll work it out later to show you what it means. And if it's not, if there's only one solution, then we have linearly independent. Okay? All right, so, but how do we check that? Well, okay, we have to solve the system of equations, which we do how? Well, we do our system, right? We put this as a matrix. Notice that the matrix is just, the columns are just the vectors. But that's very convenient, right? That these are just the vectors, and then it's a system of equations, so we have this augmented column which is all zeros. Okay, let's quickly row reduce this. That's our technique, right? So I'm going to use this pivot, so we're going to do root 2 plus 2 times row 1 to get this a 0, and then row 3 minus 3 times row 1, okay? So 1, 5, 3, and of course this is always 0, but I'll just keep copying it. 0, so I'm multiplying this with 2, and then add it to there. So 10 plus 6 is 16, 6 plus 2 is 8, 0, and then now I multiply it with negative 3, and add it up to there, 0, negative 15, that's negative 16, negative 9 plus 1 is negative 8, 0. Okay. Well, okay, I'm going to go a little bit quicker here to get to the point. Well, I need to make it so the optimal thing is to get the reduced echelon form. But I don't even need to go that far. Notice that actually these two last rows are almost the same. In fact, let's do this row operation here. Row 3 plus row 2. Okay, I agree this is not a pivot, and I should divide by 16 to get a pivot, which introduce fractions, but I kind of don't need this, because let's do this row operation. What do I get? So sometimes you can get away by this with this. So okay, get 1, 5, 3, 0, right? 0, 16, 8, 0, and then here you get 0, 0, 0, 0. Okay. So what does this mean? This is a pivot. This, if I divide it by 16, is a pivot, and that's it. There are no more pivots. So this is a free variable. This corresponds to a free variable, and we know that free variables means many solutions. And we now know that many solutions in this case means linear dependent. Okay? So that's one way of checking whether something is linear dependent or not. It's you put all the vectors into a matrix, and you think of this as a matrix, a coefficient matrix of a linear system of equations. But notice it's a very special type, right? It's a homogeneous linear system of equations. You have to get used to this word, right? You might have kind of ignored it before I was mentioning homogeneous. It refers to the fact that these are zeros. So when the column constant, the column of constants is all zeros. Okay, so let's do another example here. Let's do something perhaps in R4. Okay, let's do in R4 here. So in R4 we have the following vectors. I'm gonna V1, I'm gonna write them as columns because it makes it so much easier. 1, 2, 2, -1. V2 is the vector 4, 9, 9, -4, and V3 is the vector 5, 8, 9, -5. That's a negative here, in case this is not clear. Okay, so don't try to look at this. You cannot really see sometimes you can for simple cases, and I will say a little bit about it, but in general it's very hard to see whether something is linear independent or not. So we just have to work it out. So what does it mean? I mean, remember, we make the matrix that consists of this, and we look at it as the matrix of a homogeneous system of equations. So let me actually not even write the matrix anymore, but just the augmented matrix. So we have 1, 2, 2, -1, 4, 9, 9, -4, 5, 8, 9, -5, and then we have the zeros because it's a homogeneous system of equations, right? That's always, when we check linear dependence, it's about being the zero vector, and that corresponds to the column of zeros. That means a homogeneous system of equations. Okay. So we have to again row reduce. Okay, we have our pivot, and so the row 2 minus 2 times row 1, row 3 the same thing. I hope everybody sees how these things work now, right? And then row 4 plus row 1. So I get 1, 4, 5, 0. Times -2 and add up 0. 8 minus 8 plus 9 is 1, minus 10 plus 8 is -2. If I do it there, I get a 0, I get a 1, and now I get minus 10 plus 9 is -1, 0, and then finally just adding is 0, 0, 0, 0. Ah, okay. So we have already 1 0 row, fine, but we still have to go, right? Because if this is now dealt with, now I have to work with this guy. Sure, no problem. I do row 3 minus row 2. Okay, that gives me 1, 4, 5, 0, 1, -2, 0. And so in this row now, I'm going to minus 1 times this, and then add 0, 0. 2 minus 1 is 1, 0, 0, 0, 0, 0. Let's look at pivots again. We have 3 pivots and no free variables. So no free variables. And that, remember, if you look back at chapter 1, means a unique solution. And of course, that is the 0, 0, 0. That's the solution of this system of equations. So what does this mean is that if you want to write 0 as a linear combination x1 times v1 plus x2 times v2 plus x3 times v3, what we are looking for what this did was looking for x1, x2 and x3. What are the possibilities? And we find there's only one unique one, namely 0, 0, 0, which is always, of course, obviously 1. And so, conclusion, this means linearly independent. Okay? Get a bit used to on this terminology and what this means. So let's look at, sometimes, as I said, you can see somehow what, definitely you can see it, but so let's look in R square. If we have, well, first of all, I should say this before I even go to R square. If I have, let's look at this system. I have a vector v, v1, v2, and also the zero vector. Well, that's always linearly dependent. Can you see why? Because, remember, linear dependent, let's go back, means, where is it? If one of them is a linear combination of the others, there's a very simple way of writing one of them, hint, 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 is this guy, as a linear combination of these guys, namely 0 is 0 times v1 plus 0 times v2. In other words, if you have 0 in there, you're always linearly dependent. Okay, so that's kind of a stupid example. So let's now look in R square. And suppose we have two vectors in R square. What are the possibilities? Well, so here's my first vector. Let's call this u. And now the second vector. If the second vector lies on the same line, but remember, it could be, for instance, that it's pointing the other way, but it's on the same line. What does that mean? That means exactly that this guy, v, is a multiple of u. A certain multiple. We don't know exactly what. I mean, we can calculate it, what it is. And if it's a multiple, well, that's a special case of a linear combination, right? So if these two vectors are therefore parallel, then they are going to be linearly dependent. So if the vectors are parallel, then they are linearly dependent. Allow me to say it this way. And so what is the other thing is now any other situation. So here is this, if it is u, and now my v is not parallel, so my v is somewhere sticking out here, say, then they are linearly independent. Okay, and of course, remember the zero vector. I'm excluding the zero vector here because that's a silly case, right? So if I have two vectors that are not parallel, so okay, perhaps I should write it up here. So if it's not parallel, then it is linearly independent. That's kind of easy, right? Unfortunately, it's not always that easy if you go in more dimensions. Let's look what happens in R3. In R3, well, of course, the same is true if one vector is, it's still true for two vectors, right? Either they are parallel, then they are linear independent, and if they're not parallel, then linear independent. So that's still true. But what about three vectors now? Okay, so we have three vectors in three-dimensional space. So here we have our u, and we have our v sticking out somewhere there. Now, I don't know whether you can see from the picture, it's not three-dimensional, of course, but let's think of this, that they form a certain plane here, a plane that is not one of the coordinate planes. So now, I now consider a third vector. Here's my third vector, w here. So now what does it now mean for linear dependence and independence? If w lies in the plane, lies in this plane, in the red plane, so it lies in the let's call it the red plane, right? In the plane here, this is what I mean, this is my plane here, right? The plane spanned by u and v. So let me write it up in our notation from last time, this plane u and v. If w lies in the plane, well, then it's a linear combination of u and v. It might not be immediately clear, but that's something that we'll later see will be the case. So if that's the case, then u, v, and w are linearly dependent. Okay? If not, well, then they are linearly independent. Okay? So again, rather simple actually. to see for 3 vectors in 3-dimensional space. But the more dimensions you have, the more coordinates you have, the harder it becomes to see what it means. Okay, and so next time we will talk. So perhaps one thing I should mention, therefore, this might not be entirely clear, but suppose we have in Rn we have vectors v1 up to vm. Okay, and m and n don't need to be the same here. I'm claiming that if m is bigger than n, then they have to be automatically linearly dependent. In other words, if there are more vectors than you have space, so to speak, then there must be linear dependence among them. Okay, so just to show what this means is, well, suppose we have, I'm going to do a very simple example. Take our cube here, and suppose we have 4 vectors, 1, 0, 1, say, and we have 0, 0, 1. I'm taking some simple vectors, 1, 0, 0. These are one of the coordinate vectors here that we talked about, and 2, 1, 0. Well, think about it. How do I check whether they are linear dependent or not? Well, first of all, what I do is I look at the homogeneous system that you get, where the matrix is the columns given by the vectors. So we get these columns here. Okay. And what do you do then with the matrix? Well, you do row operations until you get an echelon form. Okay. This is a very easy one, but I'm not going to even do that. Let's think about what is the echelon form going to look like. Well, how many pivots are there going to be? Well, there can be, how many pivots can there be? Well, there can only be 1 pivot in one row. So 1, 2, 3 at most, because sometimes there is no pivot in a row, right? So like here, for instance, this row didn't have a pivot. So at most there can be 3 pivots. So at most 3 pivots. But pivots correspond to pivot variables, so at most 3 pivot variables. But there are 4 variables because we have 4 columns. So that means at least 1 free variable. Okay, one of these guys will not, so for instance, it could look something like this, right? Or our reduced echelon form could be, let's say our reduced echelon form is something like this. So this could be our reduced echelon form. Okay, so sorry, this is supposed to be sorry, that's not an echelon form. So this could be, let's say 3, and this could be 0. So this, suppose this, this is not an example, right? But let's look at another example. So after working, we could get to this case. There's the zeros, this extra column here. These are the 3 pivot variables. There can only be 3. There could be less, but there can only be 3. So this is a free variable. There's always a free variable. But free variables means, where did we say? Free variable means many solutions. Means linear dependent. Okay? So that's why if you have too many of them, they must have linear dependence. That can sometimes be easy if you quickly want to dismiss an example, one of the homework problems, say, oh, there are too many. It has to be linear dependent. Okay, so that's everything. I'm going to assign some homework problems for it. Please do not forget to leave a comment with your name when you have viewed this. Also, I have currently 20 subscribers on my channel for linear algebra, but there are more people in class. So shame on all of you who have not yet subscribed. So please do that. It's very simple. Just click on that red subscribe link. Then I know that you're part of the class. Okay? Please do that.